Hello, my name is Max Striga. Welcome to my third physics lab. In part one of this lab, I performed this lab to observe how force, momentum, distance, and gravitational potential energy are interrelated. And using the law of conservation of energy, I discovered that the mass of the black hole is 2.3 times 10 to the 34th kilograms. And this estimation is based on the speed of the star due to its induced orbit around the black hole. When I performed my experiment, I assumed that the law of conservation of energy applies to the star black hole system, which would allow me to equate gravitational potential energy to kinetic energy. I similarly assume that all measurements are accurate, meaning that all the distances and forces are based on the law of conservation of energy and do not include any outside forces, and that the star acts similarly outside of the 700-hour time frame, and that no new forces are introduced outside of the 700-hour time frame. For my procedure, I coded values for the force, momentum, energy, and velocity of the star based on existing physics principles. After this, I updated my work based on any errors. Here's my code, a portion of my code, including my force, my parallel force, my perpendicular force, my momentum derivative, and my velocity. And here's a picture of the final orbit of the star around the black hole and the mass values along with it. I discovered in part one, as I said, that the mass of the star is 2.3 times 10 to the 34th kilograms. Similarly, the derivative of momentum with respect to time is force. This is reflected in the equation F equals dP over dt, and that the law of conservation of energy applies to systems with no outside forces acting upon the system, which is of course the definition of the law of the conservation of energy. In part two of this lab, I performed that lab to observe how force, momentum, distance, and gravitational potential energy are interrelated, so similar to the first one, but I discovered that the optimal horizontal velocity of the rocket is negative 250 meters per second, and that the optimal vertical velocity is negative 750 meters per second, meaning that for the rocket to fly without any collisions, it needs to be going at negative 250, 750 meters per second. When I performed this lab, I similar to the first lab, assumed that the law of conservation of energy applies to the rocket, moon, planet system, and there are no outside forces acting upon the rocket, moon, or planet. All measurements are also accurate in this lab, and collisions occur upon tangential touch, which isn't exactly true in real life, right? Rockets can glide along a surface or crash upon just sliding due to friction, but in this lab I assumed it was true. For my procedure, I also coded values for the listed variables. I experimented with my initial velocity values for the rocket, which is very important because that ultimately gave me my working values for velocity, and I updated my work based on any errors. For my physics animation, I used this code, so I had all these listed values, and I finally added my negative 250 meters per second speed for the ship speed X on line 55, and negative 750 meters per second speed for ship speed Y on line 56, which allowed my rocket to go in the shown yellow path underneath the planet and underneath the path of the moon. Because it's in this planet-moon system, it is acted upon by both the planet and the moon, and is thus a result of their force vectors. The path of the rocket is a result of the force vectors of the planet and the moon. I discovered in part two that the optimal horizontal velocity of the rocket is negative 250 meters per second, and the optimal vertical velocity is negative 750 meters per second. And similarly, I discovered how the derivative of momentum is related to force, in that the derivative of momentum is the force, and the law of conservation of energy applies to systems with no outside forces acting upon the system.